this is going to be a very short video because what I really want to do is give a little bit of an overview of where we're going for the remainder of the semester, as well as talk about the second and one of the primary applications of the transfer function. So one of the things we can do with a transfer function is we can use it to find a frequency response. So let's go back to this example that we worked at the end of video 7-1, where we said what to do with transfer functions. And we said one thing we can do with transfer functions is we can determine the output for a given input. So in this example, we selected an input, we put it here at the input end, we transformed the circuit, and we got a transfer function, obviously in a previous example. We then multiplied that by the input, and we had this expression in the Laplace domain that gave us a function in the Laplace domain, and then we could take the inverse transform and get a solution in the time domain. I'm not sure I actually showed this slide on the last video, but I know I said it verbally. So that's one application, and it is particularly used when we have functions like this one where we have step input that turns on, turns off, so we have like multiple switches. It would be very hard to model, even though this is a simple circuit. And you know what in the world am I doing here? I think I have actually the wrong figure here, because what I really need is I need the figure for the RC. So let me come back and fix that. Let me cut this figure out and let me replace this with the appropriate RC. And let's be sure I've got the right form. S over S plus 1 over RC. So I need this one. Sorry about that. So let's come back here to this example we worked last time and correct that figure. All right, so now we have the correct figure for the transfer function. Once again, I apologize for that. So let's go back and absolutely verify that I did that right. So taking the output across the resistor, yes indeed, this is my transfer function. Okay, so we're all good now. So anyway, basically this is that RC circuit. We could have chosen R over L, we could have done, whatever. And then we got this output. So this is useful for when you have things like multiple switches, when you have capacitors that are going to charge and then discharge. And so it's a useful way to model input and output if your input could possibly change. However, one of the more common things that we use a transfer function for is to find a frequency response. So let's come back here. If you look at our output here, our output is entirely transient. So our input was transient, it was a pulse. And so we would expect, given that this is RC, that once the input voltage goes away, that the output voltage will go away. So these are transient effects. Now all circuits with sources are going to have transient effects because in Laplace we always have a turn on at t equals 0. So even if we have a sinusoidal source, we're assuming we're in the lab, we're going to turn on the power supply to deliver that sinusoidal source to a circuit. So there will be a transient effect. Now sometimes we don't care so much about the transient effects. We care more about the steady state. So after the transients have died away, which in all honesty is usually a few milliseconds or even less. So that is why the transfer functions oftentimes are used to find the frequency response, and in order to do that, we ignore the transient effects. Now remember that S is equal to sigma plus j omega. And the sigma part of S is the part of S that determines the transient response. The j omega is sort of the oscillatory part of S. So if we want to find the frequency response of a circuit or from its transfer function, then what we do is we replace S with j omega. And the resulting function is going to be a complex function of omega. Now the magnitude part represents the magnitude of the output voltage over the input voltage as a function of frequency. The phase of the complex number represents the phase of the output voltage over the phase of the input voltage as a function of frequency. So this is just an example for that RC circuit. If we replace S with j omega, now once we do this, we're leaving Laplace and we're going to a steady state analysis of something as a function of omega. So we insert j omega, we then find the magnitude of the transfer function, and we find the phase of the transfer function. So this is done on a passive network of elements of R's, L's, and C's only. No initial conditions, no sources present. So this allows us to find the frequency response of just the network of a circuit. So I go back and forth. So I'm going to pull up this next slide. The frequency response is primarily used to determine the behavior of filters, among other things. Now, one option in the class is before we look at filters, we look at how to represent transfer functions and their phase and magnitude as a function of frequency using Bode plots. This makes it easier in some ways to understand filters, but it also complicates the situation because Bode plots themselves can kind of trip students up. So I've been back and forth even this semester about whether to do Bode plots first or whether to do filters first. So I'm going to fall back on what I typically do, and we're going to work with some very simple first and second order filters built from passive components first, and then we will introduce the concept of the Bode plot and how to use it to represent transfer functions. The thing to remember is that the Bode plot is used not just for filters. It can be used for any number of things. It basically is a generic mathematical tool that gives you a visual representation of what happens to the phase and the magnitude of a transfer function when you look at its frequency response in a certain set of units. So I am going to delay the Bode plot lectures until we look at some fundamental lectures on very simple filters and talk a little bit generically about filters so that you will have sort of a frame of reference for which to understand and discuss Bode plots. After we go over Bode plots, we will go into more advanced filters and filter design, and that'll take us through the remainder of the course. The filters that are constructed from R's, L's, and C's are referred to as passive filters because they do not contain an op-amp. If the denominator of a transfer function is a first order polynomial in S, it's referred to as a first order filter. If it is a second order polynomial in S, it's referred to as a second order filter. So this semester this week we're going to work with first order passive filters, and then after the next exam we will look at Bode plots, and then we'll look at higher order filters. So that's how the rest of the semester lays out, and there is no optimum way to present the material, so I'm presenting it the way I've presented it in the past, which typically seems to make sense to students. So I wanted to post this extra video, first of all, to correct the error in video 7.1 with the figure for the transfer function, and then secondly to tell you sort of an overview of what we were going to be doing.